Hello there. This is video number 1 of section 1.9. This is actually our last section in chapter 1, and so after this we will move on to chapter 2. This is one of the most important, and I think one of the most fun sections that we're going to do. We will get to draw a lot of pictures, and I think math is always more fun when you get to visualize what's going on. But interestingly enough, I want to start off this section with a motivating example, which is a problem from the end of section 1.8. So there's a lot of writing on the board, so let's just jump right into it. We're going to let two vectors, e1 and e2, be defined as the vectors 1, 0, and 0, 1. So notice E1 has a 1 in the first position, E2 has a 1 in the second position. We will talk a lot about these vectors as the course goes on. These are called the standard basis vectors in R2. So for now, they're just two vectors, but keep in mind these two vectors, very important. Okay, and we're going to define these other two vectors, y1 and y2. Y1 is the vector 2, 5. Y2 is the vector negative 1, 6. And we're going to let t be a linear transformation from R2 to R2. And we're going to assume that t maps E1 to Y1, and that t maps E2 to Y2. Right? And so this is looking an awful lot like a problem we ended section 1.8 with, where notice we don't actually have any more information about t other than these two facts. But we're going to find, because t is a linear transformation, we can apply the properties of linear transformations to learn a lot more about t. And so this problem asks us to find the image of this vector, a, which is the vector 5, 3 under t, and the image of the vector x, which is just x1, x2 under t. So let's do A first, and then we'll do part B. So remember, we have this property that t of cu plus dv is equal to c times t of u plus d times t of v for any linear transformation, right? And so this is just for all linear transformations. And this is just one of the properties we assume about linear transformations that we can show is true. So remember, what this means is that if I can write A as a linear combination of E1 and E2, I can find the image of A by applying this property. Well, what is so nice, one of the nice things about E1 and E2, is that it's probably the easiest pair of vectors that we can look at and always figure out how do we write A as a linear combination, or any vector, really, as a linear combination of these two. Because notice, A, which is equal to the vector 5, 3, is just equal to 5e1 plus 3e2, right? 5, 3. Because notice this is 5 times 1, 0 plus 3 times 0, 1. So writing A as this linear combination, it's actually not terribly hard to see, how we might say write any vector, just arbitrary vector we would pick, x1 and x2, as a linear combination of these two vectors. So hold that thought for now. But let's go back to A. So we know that we can write t of A as this linear combination, right? So t of A, right? And so t of A, this is the image under image of A under t is this vector, is equal to t of 5e1 plus 3e2, right? And this we know from the fact that we've shown here. But because t is a linear transformation, this is equal to 5 times t of e1 plus 3 times t of e2. And so all I did was apply this property to factor out the 5 and the 3 and split up this sum. But now we know the values of t of e1 and t of e2. So to save some space, I'll probably erase the top 2 lines here. So this means that t of a is equal to 5 times y1, which is 2, 5, plus 3 times y2, which is negative 1, 6. And so t of a is equal to the vector 10, 25, plus negative 3, 18, which is the vector 7, 43. And so notice, again, by knowing the values of E1 and E2, and knowing how to write A as a linear combination of E1 and E2, I'm able to figure out the image of A just from that fact. So again, sort of this idea of learning as much as we can about T while having potentially small amounts of starting information. All right, so moving on beyond this, what about B? Well, remember I had pointed out that E1 and E2 are very nice vectors because notice for this arbitrary vector x, much in the same way we did in part A, x is equal to x1 E1 plus x2 E2, right? And this is just sort of taking what we found in part A and sort of generalizing it to any vector. Because of how E1 and E2 are defined, every vector x, which is equal to x1 and x2, can be written like this. So that means that t of x, applying our linear transformation properties, is always going to be equal to x1 times the vector y1 plus x2 times the vector y2. And actually, I'll write a little bit more out for that just to make that clear. So notice this is equal to t of x1 e1 plus x2 e2. Right, and so now this splits x1 t of e1 plus x2 t of e2. And so that's how we get x1 y1 plus x2 y2. So we actually know, and actually to save space, I'll probably erase the middle work. So again, just a quick recap of how we did this. Right, so we wrote x as this linear combination, so we can replace x by this expression in t. But remember, t can split up across sums in this way. And since we know the values of e1 and e2, we can just replace t of e1 and t of e2 by these vectors y1 and y2. And so t of x is equal to x1 y1 plus x2 y2. But let's write this out really quickly. So this is equal to x1 times 2, 5 plus x2 times negative 1, 6. Which is equal to the following matrix vector product. And so I just did something, well, I think it's cool, I guess, but you can be the judge. We didn't have a matrix for T, right? So I mean, we in section 8 we'd mentioned that every matrix is a linear transformation, right? But I actually never had mentioned the converse to that statement, right? That like every linear transformation is also a matrix. But what I just showed is that I've got this linear transformation from R2 to R2 that we didn't have a matrix for it, right? At no point did I define a matrix. I just knew what it did to E1 and E2. But what I just showed here is that the image of every vector x can be found by this matrix vector product. And so if I let this matrix be A, then T of x is actually just equal to A of x for all vectors x. So I did sort of the opposite of what we did in section 8. Using these two vectors, E1 and E2, I was able to sort of go backwards, right? I said, okay, I know what E1 and E2 do. I can now find a matrix that defines this linear transformation. So what we've learned, at least in R2, but we'll see very shortly that this applies to all linear transformations sort of from any space to any space, is that if I know what it does to the standard basis vectors in the domain, I can actually reconstruct a matrix A, which is the same linear transformation. So that is, all matrices are linear transformations, and all linear transformations are matrices. So, pretty cool. All right, so I want to generalize this. This example is sort of motivating, so you can see why I think, in R2 or, an example like this makes it a little more straightforward. We'll introduce one of the most important theorems that we've talked about thus far, and then maybe look at one more example. So the vector E sub j in, what space do I want to be in? Rn is the vector with zeros in every entry except the jth entry, which is a 1. And so this is sometimes called the standard, or the jth standard basis vector. In Rn. And so notice specifically exactly how this vector is defined depends on the space it's in. And so be a little careful. Always make sure you know what length of vectors we're talking about when you see these. For example, in R3, the vector E1 is equal to 1, 0, 0. E2 is equal to 0, 1, 0. And E3 is equal to 0, 0, 1. So it's just a vector, right? So we always have to specify, what length of vectors are we talking about? And then there's exactly n basis vectors where this index here just represents what position does the 1 fall in. All right, so given this definition, like I said, we can now introduce what is one of the most important theorems we've seen so far. This appears as theorem 10 in your textbook. And so this says, let T be a linear transformation from Rn to Rm. So we've shown that, what have we shown? We've shown that every matrix is a linear transformation. What this theorem is telling us is that every linear transformation is also a matrix. So then there's a unique matrix A such that, well, the image of every vector x is just equal to A times x, right? And that's exactly what we showed in this past example, was that, we found this matrix A such that this linear transformation was just the product of A and x. And in fact, we can take this one step further. We know what the matrix A is. It's the matrix whose columns are just given by the images of each of the standard basis vectors. So again, this corresponds to the last example. Remember, the columns of that matrix A were just y1 and y2. So what we know, and I want to end with one more example after this, what we know is that any linear transformation, if I know the images of the n standard basis vectors, I can always find a matrix A defined exactly like this, that sort of defines this linear transformation, or is equivalent, this linear transformation is equivalently defined by this matrix. And so we'll see, I thought I might get to this video, but I think it's going to be a little too long at this point, so I'll just sort of leave this for a short, kind of fun example video. That we can define linear transformations in a way that, like, initially you wouldn't at all think that we could define them using matrix multiplication. But we'll see, given this theorem here, we can always find a matrix representing a linear transformation from Rn to Rm. And so this matrix A has a name. So I'll define the matrix A is called the standard matrix for T. So this matrix A here is called the standard matrix for the linear transformation T. So if you learn one important thing, well, I hope you learn a lot of things, but remember that. How do we find the standard matrix for a linear transformation? We look at the images of all of these standard basis vectors in the domain, and we write out A correspondingly. And so notice A is in fact an m by n matrix, right? Because each of these vectors should be vectors in Rm, so A will have m rows, and there are n columns in A. And so this all checks out with what we know about how linear transformations are defined through matrix multiplication. But remember, how do we find the matrix for a linear transformation? Exactly like this. So I want to end with one example of a type of problem we can now solve. I will admit that I think every time I come back to this, this type of thing is always like the weirdest thing for me. And so like I always have to go back and remind myself that like, okay, it's just columns of the standard basis vectors. Because it's always so, I don't know, for some reason this is weird for me to think about. And like every time I read it, especially this section, I read it, it's like, oh, that's not that bad. And then I go back and it's like, none of this makes sense. So what we can do now, so suppose T is a linear transformation that maps R3 to R2. Then there exists, oh, no, sorry, I was stating the theorem again. And suppose, again, that we know the images of the 3 standard basis vectors in R3. And what we can do now is we can find the standard matrix A. And again, this, the theorem 10, which we stated in math, it's sort of a hammer in this way that, like, given this information, the theorem just makes it very easy because all we need to know, well, A is equal to the matrix whose columns are given by the images of these vectors. And so there's the standard matrix A. And so remember what this means is that any vector x in R3, I can find its image by multiplying out on the left by this matrix A. And so in that way, again, every matrix is a linear transformation, but every linear transformation is also a matrix. So, like I said, the second video is going to be relatively short. We're going to do some fun, a few fun things in R2 and look at specific types of linear transformations that might pop up a lot, especially in applications, and their corresponding matrices, which we know how to find. Then the third video for this will be kind of a big shift from what these first 2 videos have been talking about, but we will introduce, again, some more definitions, but all definitions that are very, very, very important that we will be discussing a lot this semester.